trying to understand it. We're learning it. We're making changes, see what works when you change some things, what breaks, what doesn't break. That's what we were working on. And it was hard and challenging. And we're finding that we can build all sorts of fun things in the data section, in the text section, which is where you would think, why does it have to be called text section? Why can't it be called like this, or like code, or like dot logic, right? Something like that. Because that's right, that's what it means. That's what dot text means. It actually means the instructions for the program. So we did that in previous streams, but now what we're going to do instead is we're going to make a little change. We're going to go over to this Hello Silicon tutorial, and it's got all these chapters. Look at all these chapters here. We've got a bunch of chapters that we can learn from. We're going to learn from all these chapters, you guys. So we've got chapter 1 through 16. I don't know if we're going to make it through all 16. Over from the very beginning in the Hello World on chapter 1. We're going to start in chapter 1. So sit back and strap in. Get comfy. Get cozy, you guys, because we're going to go to chapter 1 here. We're going to go to chapter 1, and we're just going to let it happen. So there's only 2 files. We don't have to worry too much about this at assembly language. And we're going to start with, it's called, what was it called? ls here, ls dot dot. It's called hello something. I needed PWD is what I need. PWD. Here we go. It's called Hello Silicon. We're going to do the Hello Silicon tutorial. This is a specific ARM assembly for ARM, basically the ARM architecture. We're going to be learning some assembly today, and we're going to start with chapter 1. In previous streams, it says assembly day. Let's open up the file, you guys. All right, so let's open up the hello world.s file, which means assembly. S for assembly. Why can't it be .as? AS sounds better. Why did they standardize on the word and the letter S? I think it makes the most sense to be assembly. Okay, so this assembler program prints hello world, standard out. Cromer, hey, good to see you, Cromer. Happy to have you here. Happy Friday. We're going to be doing some assembly, but we're going to do it in a structured way going forward. We were playing around with it before, doing all sorts of things before. Remember this from previous streams? We're in the previous stream, we did some of these things. This time going forward, we're going to do it in a structured way. So we have this hello world, hello silicon, see, hello silicon. And it's got all of these chapters in it. We're going to start with chapter 1. Okay, so let's start here. So assembler programming, let's print hello world to standard output. Hey, we're going to do some assembly code now. That's what we're going to do. We're going to jump into assembly. Okay, let's do it. So assembler, the register is x0 to x2 parameters in the Unix system calls. Okay, so these are going to be stored these are going to be used, they're going to be reserved as parameters for Unix system calls, which, of course, can be on Mac, could be on Linux, it could be on different things. It's a lot of different things that we could be on. Hassam, am I inside a matrix? I don't know what these codes are. I know it looks like the matrix, doesn't it? It really does look like. What is assembler for exits? What is assembler for exits? Assembler for exits. Okay, so right here we have actually got that. I'm pretty sure this is not what you're asking, but this is the answer that I think. So you argument 0, you put it in your register, you put 0 in a register, so it's just literally the number 0, and then you have a system call and service, and then you have for the return code. In x16 you're going to say number 1, which is just the literal number 1, and that's the system call to terminate the program. And then you say CSV to terminate, right? Which then puts x0 and x16, and then it knows they're good, you guys. We're going to be doing assembly. We're learning today from a guide now. It's called Hello Silicon. It's called Hello Silicon, and you can search this. It's a GitHub repository that has 16 chapters that gets you up to speed on ARM64 Apple Silicon assembly, and that's what we're doing. That's what we're doing, you guys. Go, you guys. We're going to do it. All right, so let's do the start. We've got to start. This is an interesting format. This is very interesting. All right, so start. You can name this whatever you want, but it depends on your makefile or however you build it, right? So we learned this in previous streams. So /_start. I think you can change this. So estart, we can call this eweeb. Let's do that. Let's change it to weeb. Let's do it, and let's make sure this works. Weeb. I'm pretty sure that'll work, you guys. Jack Keeble, what are we working on today in assembly? Okay, so we've got this Hello Silicon right here. We've got this Hello Silicon. You can see here at the bottom of the screen. Hello Silicon. It is a tutorial that is a GitHub repo that has 16 chapters. we've been playing around with assembly for the past few streams, and today what we're going to do is we're going to learn more methodically using some pre-existing materials. So we're going to start in chapter 1. We're going to start over from the beginning, and we're going to get cozy. We're going to do assembly today. We're doing assembly, and we're learning from a tutorial today. Is that the Easy 68K compiler? Oh, actually, I don't think so. So we're not using a compiler. We are using an assembler, and we're using a linker because we're only writing assembly. We don't need a compiler, you guys, because a compiler will compile to assembly, and then an assembler assembles assembly code to machine code, and then you use a linker to take that machine code and then link it up to all the operating system things. Whatever the linker does. That's what it is. Jumping back into this, sorry. So we've got register 1. Basically it says set x1, which is usually used for arguments and parameters, to number 1, which is going to be standard out because we're going to call service. We're going to call service, and this is x0 is one of the arguments for service to represent what we're going to call in the service. So standard out is a static number. It's a static enum, basically saying that we're going to be calling standard out. And then x1 is going to be the, I believe, let's see here, string to print, and then length of our string. Okay, 13 is the length. How do we know it's 13? We got to check this out, guys. We got to check this out. So move2 is going to be, x2 is going to be the length. x2 is the length of our string, x2, and it's hard-coded to 13. Number 13, it just means literally the number 13, which is going to be the length of hello world. See, let's actually count it. Here we go. Let's count it. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's 13 characters, and this \n counts as 1 character. Even though it's 2 characters on the screen, it only counts as 1 character, you guys, right here. 1 character. This \n. So it's 13 characters here. You see? 13 characters. Wow, who would ever thought? Okay, so the length of our string. There we go. Are there tabs? There's tabs in here, aren't there? That's what's going on. It's the tabs. There's tabs in here. That's crazy. Who uses tabs anymore? Do you guys use actual tabs or spaces? Tabs or spaces? Obviously, the answer is spaces, because it works universally in all text editors. Spaces are guaranteed to have the same indentation, no matter how many characters are involved. So spaces are really, really useful. That's why you don't need .data before you did. Okay, before your data, it's recommended, because everything after data can't be executed by mistake. Oh, but we'll exit the program. So it's best practice. So we should do .data. We should do .data, and we should put our hello world right here, like that. We should be doing it because it's best practice. Otherwise, it could be used as buffer overflows to set up a program in RAM and then execute any code inside of your program. Let's see if this builds. I think it'll build. Make. Looks good to me. Let me say ./hello, and it's going to print bus error. Wait, it's going to print bus error. We might have to change the make file, you guys. We might have to change bus file. And then you see if we can undo. Let's go back to the beginning of time. We're going to save everything, and we'll rebuild it. Rebuild it. Make. Wait, so for here we go. We'll say start. Here we go. Let's see if we can make it. Okay, it builds. All right. Hello. Is it going to... Hello, world. We did it. Okay. What did we break? How did we break it? I don't even know what we did. Maybe because of this right here. It might have been this, you guys. It might have been this. This is why we broke it. It could have been this right here. So ADR, string to print. So what does ADR do? ADR does not need to relocate, or ADR gets address of the label. Okay, so x1 becomes the address for the label. Okay, is x1 ever used again? See, this is where I don't get it. Like we've got, oh no, I do get it, because we're calling a service here. We're calling a service, says we're going to set this number 1, which is when you call a service, x0 is going to call this, which is a static. This is a static data. Like there's a whole bunch of numbers on system calls that you can use, and number 1 is standard output. You're going to print something. That's what it's going to be. Your call, SVC. It's SVC, supervisor call. It switches control of your program to the supervisor, which is the operating system. The context OS is the supervisor. You guys, we're learning new things today. We've learned something new already. This is so cool. Shimon, thank you. Thank you so much. Here, check this out though. I did a thing. I moved the data. I moved it here, but it doesn't like it. Why doesn't it like it? Why is it having an issue? it says bus error. It is having an issue. It likes the data to not be there. I wonder if it's like this. Is it going to work here? Let's do make and if it passes, we'll say ./hello. See, it doesn't like data. Oh, because I have to do this. Here, check this out. .text, right? Is that what we have to do, Shimon? Is that what we have to do? Now it'll work, right? Now it'll work. Is it going to work now? Nope, just kidding. That doesn't work. That does not work. I don't know why. I don't know why. What's going on? What's wrong with this? This is weird. The CPU gets data through the bus, a fixed amount of wires. Okay. Some instructions need all the data to come through at once on the bus. If data is on the boundary of the bus, it can't be used. Oh, then we just pass x80 to call to the kernel to terminate the program. That's what x80 is. Wait, no, 1, 0. Wait, no, x16. Wait, hold on. Wait. So move x1 is going to be 1 for standard out. We're taking the x1 here is going to become hello world, which is the address. So it's the memory pointer. And then we say move x2 is the third. Okay, so we've got three parameters here. We've got 3 parameters, x, 0, 1, and 2. 3 parameters, you guys, 3 parameters. Okay. With these 3 parameters, we're going to be passing into the supervisor call here. But we also have x16. And x16, I don't understand what's coming on with x16. I do not get x16 here. Unix write system call. See, should always be a line 4. Okay, code should always be a line 4. So that means we should always be a line 4 on code. Okay, that's good to know. ARM64 has 30-bit instructions, so it should be aligned 4-byte boundary. Okay, so we'll always make it 4. So because we're in code now, which is here, I think, can't we say .text? I'm pretty sure we can say text right here, right? Can we say text like that? Does that work? No, it doesn't like that. It doesn't like it, you guys. What if we did put it there? Can we do that? Is it like? Nope, doesn't like that. What if we get rid of it? Is it good now? Nope. Hold on. Okay. What is going on here? Oh, because we did. Okay, there we go. Now, is that going to work? No, it doesn't. Wait, 2? Wait. No, hold on. We delete. Oh, we doubled up on it. That's what we did. That's what we did, you guys. All right, so let's bring this back to a line 4. We'll bring it back to a line 4, and then let's make sure that it builds. Yep, it builds, and we're good to go. Okay, cool. 4-byte, not 4-bit. 4-byte, not 4-bit. Okay, good to know. Good to know. It's 4-byte, not 4-bit. Inserts 0 until address is aligned to the boundary, divisible by the number you provided after a line. A line 4 is aligned to 4-bit boundary. Okay, okay, that's when you said 4-byte, not 4-bit. 4-bit boundary. Okay. Chrome 16. This is important. I've been curious about this because x16 here, and then x16 is here as well, right? So we've got x16 in 2 spots, right? So we're looking at the 2 different spots where x16 is at. What is the deal? Why x16? Okay, let's see if Simone has got the answer for us. Thank you for the likes, you guys. Appreciate it. x16 tells the OS it should do. Thank you for the likes. Appreciate it. You can see the little heart icon showing up there on the screen. The OS, what should it do during this the supervisor call? Oh, that's what x16 is. If you do x16 equals 4, it prints, it writes to standard out, or writes to a file. If you do x16 equals 1, it exits. So we've got 4 parameters here. We've got 4 parameters before we call our supervisor. X1, which aligns to hello world, which is going to be the address of the pointer of the string. It prints, writes to standard out, writes to file. Oh, or writes to file. Okay. Okay, you get the numbers from a table. Yeah, I found the table. Simone, I found the table. Yes, x0 is the file descriptor. Okay, cool. 1 is the file descriptor for standard out. Okay, yep, that makes sense. So we got this. So x0 is going to set to 1, which is the file descriptor of 1, which is standard out, which means it's going to print on your terminal window. That's pretty straightforward. X2 is going to say how many to print. So if we chain this down just to 5, we should see just the word hello and not the word world, right? Is that what we should see? We should see just the world, just the hello world is what we should see. We won't see world. We'll just see hello. Let's try it. Okay, so we run it, make it. We'll see. Yep, we did it. You guys, look. Hello. Right here. We did it. Hello. Boom. Hello. Right here. Boom, boom, boom. Hello. We did it. Okay. But remember, all of them, x0 through x29, are just normal registers you can use for normal math. The OS just expects some parameters in specific registers. We get this. And so now we print, and now we have x0, which is going to be 0. Used for 0. So this is the input into the service call, the first parameter. Thank you for the likes, you guys. Appreciate it. And then we've got x16, which is going to be you set based on the number, which is number 1, which is going to be exit. This terminates the program. This terminates the 1. And we know 4 is for writing to the system, right? 4 is writing. So we need to see all the SVC table. We want to see SVC. We're learning some assembly. We did chapter 1 in what's called supervisor call. We know that x16 is where you call the table lookup for what the service call is actually going to perform, right? x16, we're going to do number 4. Number 4 means write. It means output, write the string. And we're going to write it to the file descriptor number 1, which is standard output. And we're going to move the address to x1 of hello world variable, which is down here, hello world. And then it has this number of characters to print, cd chapter 1. I think we did really good on chapter 1. Let's see, hello world.s. Yep, here we go. Very simple, a very simple program. We did it, you guys.